Okay, welcome to GADEP's Geometry, Arithmetic, and Differential Equation of Periods. Today we have Cristiana Bertolin, who is going to talk about the Grothendieck period conjecture and one motifs. Okay.
So first of all, thanks for the invitation. So I will speak about Grothendieck period conjecture applied to one motif. So I recall that Chanuel proposed the following conjecture. So we take x1, xn complex number, linearly independent over Q. Then he said that at least n of the number x1, xn, e to the x1, e to the xn are algebraically independent over Q bar. This is the so-called Chanuel conjecture. This conjecture is very clear, very easy to write down, but it's a very difficult conjecture. It is an open conjecture, except for two cases. The Lindemann-Weierstrass theorem, which say that if x1, xn are algebraic number Q linearly independent, then e to the x1, e to the xn are algebraically independent over Q bar. And the second case is the Hermit-Lindemann theorem, which is just the Chanuel conjecture for n equal to 1. We can, in some sense, generalize this conjecture. So the exponential function is just the exponential function for the multiplicative group Gm. So it goes from the Lie algebra of Gm to the C complex point of Gm. And we have an analog function for the elliptic curve. We can construct the exponential of elliptic curve using the Weierstrass P function relative to the lattice. So this function depends on the basis of the lattice that we choose. And so we go from the Lie algebra of A to the complex point of the elliptic curve that we embed in P2. So to Z, we associate the projective point 1, pz, p prime of z. P prime of z is the derivative of p of z. So we have an elliptic analog of Lindemann-Weierstrass theorem for elliptic curve. This is a theorem proved by Philippon and independently by Brustol. And they show that if we take alpha 1, alpha n algebraic number linearly independent over the field of complex multiplication of the elliptic curve, then the number p alpha 1, p alpha n are algebraically independent over Q bar. So this is the elliptic analog of Lindemann-Weierstrass. So in a much more general context, Grothendieck has proposed a conjecture which gives more ambitious prediction. First of all, in his paper ES 29, Grothendieck has proved that the first Theorem cohomology group of an abelian variety and its first Betti cohomology these two groups are isomorphic, and this isomorphism is just given by the integration. So you take a path and a differential form, and you integrate this differential form along this path. And if you choose a basis of these two vector spaces, you can build a matrix which will represent this isomorphism. And the entry of this matrix are the so-called period of an abelian variety. I have write this for an abelian variety, but it is true in a much more general context. So the period are just the integration of differential form of the first and second kind. This is the omega I and the eta I along the 2G path gamma I. So always in this paper, Grothendieck state that, in fact, any polynomial relation with rational coefficient between the periods of A should have a geometrical origin. He say only this. He was not very precise. Several years later, Long, in his book Introduction to Transcendental Number, was more precise about this conjecture. He said that any algebraic cycle on A and on a product of A with itself will give rise to polynomial relation with rational coefficient among the periods of A. Grothendieck conjecture is that the ideal generated by this polynomial relation is an ideal of definition of the period matrix. This means that all polynomial with rational coefficient which has the period has 0 should come from algebraic cycle. This is a very difficult conjecture because in the literature I never there is no proof of this conjecture, but nobody has showed that an algebraic cycle give a polynomial relation. Just the link in his lecture note 900 show how to get Legendre relation, which is a polynomial relation between the period of an abelian variety, and he show how to get this polynomial from an algebraic cycle. But so far as I know, it is the only place where, starting from an algebraic cycle, we get a polynomial. So just also the first sentence here is wide open. Then the conjecture say that all polynomial relation comes from algebraic cycle, but it is also very difficult to start from an algebraic cycle and to found a polynomial relation. So several years later, Yves André, using the notion of motivic Galois group, proposed the following way to write down the Grothendieck conjecture. He said that if X is a smooth projective variety over Q bar, then the transcendence degree over Q bar of the field over Q bar generated by the period of X, this transcendence degree should be equal to the dimension of the motivic Galois group. In the case of an abelian variety, the motivic Galois group is isomorphic to the Montfort-8 group. And this conjecture is related to what I've said, Grothendieck, because the dimension of the motivic Galois group is strictly related to the existence of algebraic cycle. In fact, Grothendieck period conjecture is the above equality, that is the transcendence of the field generated by the period of X should be equal to the dimension of the Montfort-8 group of X, plus the connectedness of the period torsor. But in number theory, when people say Grothendieck period conjecture, they mean just this equality here. They don't never speak about the connectedness of the period torsor. So we will just study this equality here. So in order to study, I have to show some period. I want to construct the period, the matrix period of one motif. So I start with the differential. I recall that a differential is of first kind if it is everywhere holomorphic. It is of second kind if the residue at any pole vanish. And it is of third kind in general. And obviously, differential of first kind are contained in differential of second kind, and they are contained in the differential of third kind. In the case of an elliptic curve, I want to show how I want to compute this differential. So I take an elliptic curve over C with Weierstrass coordinate function x and y, and we have the lattice. So I recall that we have the Weierstrass P function, which is a meromorphic function having a double pole with residue 0 at each point of the lattice. Then we have the classical sigma function, which is holomorphic everywhere. And then we have the zeta function, this one, which is meromorphic with a simple pole at each point of the lattice. So now I want to construct the differential form on the elliptic curve. So the differential form of first kind is well known. It is dx over y. And the pullback via the exponential map of this differential form is just dz. The differential of second kind is also well known. It is x dx over y. And it has a double pole with a residue 0 at each point of the lattice. And its pullback by the exponential map of the elliptic curve is just the Weierstrass P function multiplied by dz. These are well-known differential form. What is less known are the differential form of third kind. These are of this type, CQ. This differential form of third kind depend on the point of the dual elliptic curve. So CQ is 1/2 y minus y of q over x minus x of q multiplied by dx over y. So for each point of the dual elliptic curve different from 0, you get a third kind integral. If q is an elliptic logarithm of pq, the pullback via the exponential of the elliptic curve of this differential form is f prime is the f prime qz over fqz dz, where fqz is a self function. Fqz is sigma z plus q over sigma z sigma q multiplied by e to the minus zeta qz, with q an elliptic logarithm of big Q. So this self function is the differential logarithm of the differential logarithm of self function is just the pullback of this differential form of third kind. So if now we choose two paths on our elliptic curve, we have, this is well known, the elliptic integral of the first kind that we write down omega 1 and omega 2. And we know that these are the period of the Weierstrass P function. P of z plus omega I is just P of z. Then the elliptic integral of second kind, what we call normally eta 1 and eta 2, are the quasi-period of the zeta function. So zeta of z plus omega I is zeta of z plus eta I. So Michel Waldschmidt was interested in the elliptic integral of third kind, and so he discovered that the exponential of the elliptic integral of the third kind, which are, so if I integrate CQ over a path gamma 1, I get eta 1 Q minus omega 1 zeta Q. So the exponential of this elliptic integral of the third kind are the quasi period of self function. This means that the fq of z plus omega 1 is equal to FQZ multiplied by the exponential to the eta 1q minus omega 1 CQ. So the elliptic integral of first and second kind are period, but in the case of elliptic integral of third kind, you have to take the exponential of them in order to give them a sense of a period. So now I want to make a link with one motif. So what is one motif? So one motif defined over a subfield K of C. We write it in this way. M is equal bracket and narrow from a 3Z module to G, where G is an extension of an abelian variety by a torus. Torus is a power of the multiplicative group. This should be defined over Q. Remark that such an extension of A by GMS is parameterized by a k-rational point of the dual abelian variety, because the dual abelian variety can be seen as the X1 AGM. And these extensions are also called semi-abelian variety. Then on such semi-abelian variety G, we fix some point. So the arrow U is just in order to fix R point, R1, Rn in this extension, which live above some point of the abelian variety, because here you have the projection of from G to A. As we have seen the last slide, differential form of third kind involve points on the dual elliptic variety. But this point related to the differential of third kind are also the point which parameterize the extension of A by GM. So extension of an abelian variety by a torus are related to point of the dual abelian variety, and with this point you also can construct differential of third kind. So extension correspond to a differential of third kind. So now I want to construct the period matrix of one motif. So I choose a differential form of first kind of an abelian variety A, of the abelian variety underlying the extension G. Then I choose the differential form of second kind on A. And then I choose a invariant differential form on G, which induce the invariant differential form, the classical invariant differential form on the toric part. This means on the torus GMS. And we construct this differential form on G via the pullback of the differential form of third kind CQK on A, where I recall QK is a point which parameterize the extension G. Then we choose loops on the abelian variety, gamma 1, gamma 2G, and we lift these loops on A on G. This is possible. And then we take a basis of the homology of the torus. And in order to conclude, we select a path from the origin from the origin of G to the point Ri, which live in G. The point Ri live in G, and they live above the point Pi in A. So now we have all this differential form. We can integrate, and we get the period matrices. So in the case of an abelian variety, it's the classical period matrix. You found them also in the first page of Lange-Berkenacke. Then the periods of G are the period of A plus 2 pi I. And then you have to add the integral of the differential form of third kind coming from A along the pullback of the path gamma j of A. If you want the matrix period of the whole one motif M, you just you take the period of G, and then you have to add the generalized semi-abelian logarithm of the point R1, Rn. These semi-abelian logarithms are just, I recall that the point Pi, the point Ri project on the point Pi because we have an arrow from G to A. So these generalized logarithms are first the integration from the origin to pi I of the differential form of first kind. Then you integrate from the origin to pi I for the differential form of second kind. And then you integrate from the origin to Ri the differential form of third kind. So you see that the field generated by the period of A is contained in the field generated by the period of G, and it is contained in the field generated by the period of M.
Cristiana, one question. The differential form of the third kind, the pole locus of these guys are PIs or something else? The polar.
The pole of this of the Xi.
Yeah, exactly.
We go back.
Because in the elliptic case, it was O and the point that you fixed. But in this case?
No, the polar no, Q is not a pole. The integral of the third kind of are this one.
Yeah, but for example, in this case, it has pole at infinity, and that also in this point in Q.
Yes, because it is the divisor associated should contain the point Q. Yes, but also the construction is the same also in the case of an abelian variety. You just have to, instead of the sigma function, you have to consider the theta function.
Okay.
You construct, in the case of an abelian variety, you construct a big F of Q, depending always on the point. And instead, it's really the same definition. And instead of sigma, you take the theta function.
Okay, thanks.
But the pole, yes, you are right. The pole are the Q, the point. Yeah. So in the case of an elliptic curve, things are much more explicit. We just take an extension of elliptic curve by just one torus, GM. And so this is parameterized just by one point. And explicitly, so you see, the first who compute this matrix is Daniel Bertrand. So you have in the middle the period of the abelian variety. Then we have 2 pi I, the period of the torus. Then eta 1 q minus omega 1 zeta q and eta q minus omega 2 zeta q are the period due to the extension. And in the first line, we have the generalized logarithm of the point R, which involve the logarithm of P, zeta P, and the logarithm of this serve function evaluated in P. So this is the first line is the generalized, the contribute to the period matrix of the point R. So Grothendieck conjecture, as we have seen, has an equality, but in Shanwell conjecture, we have just a lower bound. So in fact, the Grothendieck conjecture, as we have written it, is not enough. And Yvonne Rey has generalized it in the following way. So if M is a pure or mixed motif defined over a subfield K of C, the difference you see is that we are no longer working over an algebraically closed field. So it's any subfield K of C. Then the transcendence degree of the field generated over K by the period of M is bigger or equal to the dimension of the motivic Galois group of M. One motif are not pure motif, but they are mixed motif, because an abelian variety is a pure motif, a torus is a pure motif, but if you take an extension of an abelian variety by a torus, you get mixed motif. So they are no longer pure motif. For me, pure motif are motif whose Hodge realization are pure, are Hodge structure. Mixed motif are geometrical objects whose Hodge realization are mixed Hodge structure. And abelian variety tori are pure Hodge structure. One motif give mixed Hodge structure. This is the difference for me between pure and mixed. So this conjecture contain Shanwell conjecture and also elliptic analog of Shanwell conjecture, semi-elliptic analog of Shanwell conjecture. So it's much more general than the first conjecture of Grothendieck. And the generalization is that we don't suppose that the motif is defined over Q bar. It can be defined over any subfield K of C. Now, as you see in this conjecture, now we know which are the period of M. We have to compute the dimension of this motivic Galois group. Or as in the case of an abelian variety, the motivic Galois group is isomorphic, we can say, coincide with the Montfortet group. So if you don't know what is a motivic Galois group, you can write here instead the Montfortet group of M. In the case of one motif. So if we consider a one motif M, so I recall G is an extension of an abelian variety by a torus, then we fix some point on this extension G, we call them Ri, and the projection of this point in the abelian variety are the Pi. So we have that the Montfortet, the motivic Galois group is an extension of the motivic Galois group of A by the unipotent radical of the motivic Galois group of M. And it's because the motivic Galois group of A has the Montfortet group of A is the larger reductive subgroup. So these short exact sequences, the usual one, you have the reductive part and then the unipotent part. And this means that the dimension of the motivic Galois group should be the sum of the dimension of the motivic Galois group of A plus the dimension of the unipotent radical of M. So now what we have to do is to compute the dimension of the unipotent radical of M. In general, so far as I know, we don't know the dimension of the motivic Galois group of A for an arbitrary abelian variety. I know how to compute this dimension in the case of elliptic curve, obviously, but also a product of elliptic curve. Perhaps in the literature, we can find the dimension of the Montfortet group for some very special abelian variety. But in general, I think we don't know this dimension. But we can compute explicitly the dimension of the unipotent radical of M. We proceed in this way. So we note P, the point P1, Pn, living in An. Above the point PR lives the point Ri. And then we note Q, just Q, the point Q1, Qs, which parameterize the extension G. We note B, the smallest abelian subgroup of N cross A star S containing the point PQ, modulo isogeny. Then we note BQ, the fiber of in AN of B above Q. This is just B intersect with AN cross Q. And obviously it contains the point P. Then we take n copy of the extension G. So Gn is an extension of An by Gm and S. Here leaves the point R1, Rn. And then we consider the pullback of Gn above PQ. This is possible to do it. And we call this pullback by this inclusion E prime. And then we note R tilde, the point corresponding to the point R. And then we denote Z, the smallest subgroup of the torus GMNS, which contain all the data that you need to define R tilde, such that R tilde belongs to the torsor E over BQ with fiber Z. In some sense, you choose all the fiber that you need in order to get R tilde. So this last part is quite technical, and it involves veil pairing. It's not so easy. But in some sense, you take the smallest torsor containing all the data that you need in order to construct R. These are the idea. With this notation, we have that the dimension of the unipotent radical of M is 2 multiplied by the dimension of the abelian variety B generated by the point P1, Pn, Q1, Qs, plus the dimension of the torus that we have constructed. In the case where we don't have an abelian part in the one motif, our one motif is just an arrow. We can write it as an arrow from Z to S copy of GM. And this arrow is just given by S point in K star. And this is one motif, what we call a one motif without the abelian part. And in this case, the dimension of the motivic Galois group of M is the dimension of the motivic Galois group of the torus, which is just 1. And the dimension of this torus is what I call dimension of log, where log is the Q sub vector space of C modulo 2 pi I generated by the log Qi for I from 1 to S. So the unipotent part, the unipotent radical part, is really controlled by the point R. Is really related to the point R that you have choose. So with this notation, I want to show that Schanuel conjecture corresponds really to the generalized Grothendieck period conjecture applied to one motif without abelian part. In fact, generalized Grothendieck period conjecture, it's a conjecture that you can apply to any geometrical object. It's not true only for one motif. But if you apply it to one motif, you really get Schanuel conjecture. I want to show how things work. So now we prove that Grothendieck implies Schanuel. So we have to show Schanuel. So we start with x1, xn, Q linearly independent complex number. We set Qi is e to the xi, and we take as a field of definition of the one motif just Q, just the field generated by Q1, Qn over Q. Now we can construct one motif defined over Q in this way. We take Z and n copy of the torus GM, and we define U sending 1 in the point Q1, Qn that we have defined. In this case, the period matrix is very easy. So we have 2 pi I are the period of the torus, and the generalized logarithm of the point Q1, Qn is just log Q1 log Qs, because in this case you have just the toric part. Now, if 2 pi I is not one of the xj, then since x1, xn are Q-linearly independent, the dimension of the Q subvector space log is n, since it is generated by the log Qi. Now, by the generalized Grothendieck period conjecture, we have that the transcendence degree of the field generated over Q by 2 pi I xi and e to the xi. This is the transcendence degree of the field generated over Q by 2 pi I, the xc. Xc are the log of the Qe, and then we have the e to the xc are the Qi. And this is exactly the transcendence degree of the field generated by the period of M over Q. This should be, since we assume Grothendieck conjecture, we know that this is bigger or equal to the dimension of the motivic Galois group, which is 1 plus the dimension of the what I've called the log, which is n. And so we get, since we can now drop 2 pi I, since all the xi are different from 2 pi I, we delete 2 pi I, and so we delete the 1 here, and we get exactly a Shanwell conjecture. In the case in which, so we assume that 2 pi I is one of the xi, so we put 2 pi I is equal to xn, we proceeding the same way, just setting Q1 is equal to a to the x1 and Qn minus 1 e to the xn minus 1, since 2 pi I appear already has a period because it is a period of the torus. So we have to consider one n minus 1 points in the torus. So this is how we proceed from Grothendieck to Shanwell. We do in the other way. We have to show Grothendieck in the case of one motif, assuming Shanwell. So we start from one motif. So this is a 3Z module and the torus, and the arrow from the 3Z module to the torus. So this arrow are just a point in K star, and we assume that the field over which M is defined is just the field generated over Q by this point Qej. The period matrix of M is as before. You have 2 pi I, and then you have all the logarithm of the point Qej. If we denote D the dimension of the Q subvector space of C generated by the period of M, and we let x1, xd a basis of this Q vector space. Now we apply a Shanwell conjecture to this Q linearly independent complex point, x1, xd, and we find that the transcendence degree of the field generated over Q by the period of M is equal to the transcendence degree of the field generated over Q by 2 pi I and log Qej, and I have to also to put the Qej because they belong to the field of definition of the one motif. And I know that this is equal to the transcendence degree of the field, transcendence degree of the field generated over Q by the xi e to the xi. And by Shanwell, we know that this is bigger or equal to D, and this D is 1 plus dimension of the vector space that I call logarithm, and this is exactly the dimension of the motivic Galois group of M. So in this direction, we have shown Grothendieck applied to one motif without Abelian part using Shanwell. So the Shanwell conjecture is really the Grothendieck period conjecture, the generalized Grothendieck period conjecture applied to one motif without Abelian part. And if you apply the Grothendieck period conjecture, the generalized Grothendieck period conjecture to other one motive also involving, for example, abelian variety, you get a lot of conjecture that we call the elliptic analog of Shanwell conjecture, the semi-elliptic analog Shanwell conjecture. This is a way to construct a lot of conjecture, but obviously it's not very, you can prove them. It's very difficult, at least. I'm able to write down conjecture, but not really to prove them. So. Finally, I want to show this result concerning algebraic independence. If I have two extension F1, F2 of a field F, we call these two extension free or algebraically independent over F. If any finite set of elements of F1, which is algebraically independent over F, remain so over F2. So if we consider semi-abelian variety defined over Q bar, and we denote omega G its period matrix, we construct two towers. So the first one, we start E0 is just the algebraic closure of Q, and then we construct En using the component of the exponential of the point living in Lie the G of the Lie algebra of G evaluated in En minus 1. Then we construct the tower L. So L0 is the algebraic closure of the field generated over Q by the period of G. And then Ln is the field generated by the period of G and the component of the generalized logarithm of point living in G Ln minus 1. And with Patrice Philippon and Sa, Ekata and Biswajotti, we have showed the following result. So if we set E the union of all the En and L the union of all the Ln, then if we assume the generalized Grothendieck period conjecture, we have shown that the field E and L are algebraically independent over Q bar. This means that any finite set of elements of E, which is algebraically independent over Q bar, remains so also in L. This definition of free or algebraically independent doesn't seem symmetric, but in fact it is symmetric. You can write, you can change F1 with F2 and it remains true. So I finished my talk. If you have any question.
Okay, thank you, Christina. Any question? I will stop recording. I just don't know.